So you have a function and you can expand it into the form of polynomials? Cool! But what exactly is it, and why do we have to use these long formulas, and how is it even useful in the first place? Let's have a look at some example functions, like e to the x. As you can see, we can transform e to the x into some seemingly random infinite series. Or sine of x or cosine of x, just to name a few. Even though not all functions are expandable by using Taylor series, it is still proved useful. For instance, if you ask to evaluate cosine of 0.28. Okay, so now that we make sure that we are on the same page, let's dive deeper into how it is done. If we take a closer look at a point, let's say 0, 1, we know that cosine of 0 is 1, so our polynomial should be 1 as well. But if we plug in other x values, we would still get 1, which doesn't make any sense. In this case, we should consider its first derivative, because if the functions are going to be equal, then their rate of change might as well be equivalent. And since the first derivative of cosine is 0 at point 0, it also means that our polynomial doesn't have the term x, or in other words, it's just plus 0x. At this point in time, we have what's commonly known as a linear approximation, which is just a line, but we want it to be more accurate. That's why we're putting in more terms by looking at a higher order derivatives, which is 2 for our next one. Repeating everything we have done again, look at the second derivatives of both the polynomial and the function cosine. But due to time limit, I'm gonna just give you the answer that the term we are looking for is just minus x squared over 2 factorial. Now you're starting to see that as we keep adding more and more terms by looking at higher and higher order derivatives, give us even more precise approximation of the function. Isn't it surprising that the only thing we need to know is just how to take the derivative of a function and the fact that it is a rate of change?